What is up, sports fans? It's me, Spencer, back with the second part in our series on explaining complex LLM topics in a way that even I will understand. And if I can understand it, you definitely can. Last session, we picked up and we talked about the concept of prompt scaffolding. Here's a quick refresher on what that is. You might remember our previous video where we explored two concepts to understand what prompt scaffolding is and why it might lead to poorer outcomes for you and your product. Quick refresher, we've got two programs, both of which are designed to roll dice. There's a key difference between the two of them though. The first one is just an LLM call, right? We have told our LLM this. The second does this programmatically using Python's randint function. What do you think the difference is? What do you think the different outcomes of these two will be? Pause the video, get back to me. If you said that one of them will return a language response and the other will return a series of numbers or integers, you are correct. So here's the key difference between these two. The first one is simulating dice rolls as a language response. We're getting a probabilistic output for what rolling dice might look like. The second is using a pseudo-random number generator to actually give us a series of numbers corresponding to the numbers of times we'd asked it to roll the dice. If that sounds complex and you're not sure why that matters, here we go. So the first one, imagine you were building a system that asks users, how many do you want to request a refund? And they go, yeah, I want to request a refund. And you've just used an LLM call to do that with nothing else. And you get a language response. And that language response goes, I've processed your refund. Here it is, enjoy. They've not actually gotten a refund. You've just made it look like they have. In the second case, we've actually done the thing. So imagine your system was asking people if they want a refund and then you go away and you do it programmatically. They've actually got the outcome they want. And this is a really core concept. So when we're prompting, we need to understand the role of tool calls. The third example that we've got here uses LangChain to invoke a tool. So we're treating the second one as a programmatic tool. So our LLM has access to this, call it skill, whatever you want. It's just a tool call. So using LangChain, we can string this together with our previous request and give the user what they're looking for programmatically, right? Useful, huh? You might find that, let's say I only want to have my LLM roll dice when I'm absolutely certain that a user has rolled dice, right? Like I want to make sure I'm only programmatically calling for a dice roll when I'm certain that they've issued an utterance that's going to trigger a dice roll. And this is a carryover concept from old school conversation design where we're using like deterministic flows. You'd map utterances to outcomes as part of your intent mapping, right? Now that we're working in a multi-intent environment, the way we approach this is really different. And normally we'll think, oh, well, how can I address this in prompting? And you might think to yourself, right, well, it's simple, right? I'll just use the prompting. I'll go, you are a dice roller, la, 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 la. Always get a deep understanding, a deep contextual understanding of the user's intent in this case. And only roll dice if the user specifically says they want you to roll dice. Seems sensible, right? And sometimes you might find that this works. You might find that you're getting an outcome that reflects this, that the thing's being more careful about when it rolls dice. It goes through a flow, a language flow, like capturing the user intent. It goes, oh, do you really want to roll dice? Yes or no, yes or no, you go through. Where you're going to find that this falls through is if you do it at scale. And using this sort of solution at scale, well, you'll see inconsistencies. You'll see that the LLM might be, really erring on the side of caution with those dice rolls. It's not rolling the dice. It's going, no. Why is that? Well, I'm going to unpack some work that I've done recently and use that to show you kind of what the concept is here, what's going wrong, and explain one core component of our prompting, which is task pattern recognition. And associated with that, task pattern. Let me explain task pattern with a quick anecdote. Imagine that I've got builders in. I've told them I want an extension and I want it like Le Corbusier. And they go out there and they do some work and I get what they think looks like a bit of Le Corbusier's work. I've left a lot to chance. I've not really given them the images to work with. I've not really given them, plans from an architect. I've not really given them even a mood board, for example. I've let them get to work based on what I've told them. And they've extracted meaning from my words and they've mapped that to what they think it is and they've gone to do it, right? Imagine I've given them a full set of plans combined with a list of things to do, step by step, ingredients that I want, items that I want, and when I want to put it in. I'm going to get a better job out of them because I've given them a sort of choreography to follow that follows my mental plan, no? You're still with me? Right, okay, so on to the concept 2. This is something I've been working on recently, and the concept is that we've got some complicated data in the back end that we want to pass through our LLM in an easy to read way. So prettified, nicely stylized. We don't want just a block of text. We want to hand it over in a nice formatted structure. Then we want to give our users the opportunity to interrogate that information. So ask some follow-up questions, unpick it and see what's going on with it. We want it to look like this, in effect. How are we going to get to this, right? We know that we've got 2 things going on here. We're going to pass the data from the back end for an LLM interpretation, right? And then we're going to use that strict JSON response that we're getting from the LLM, enforced by Pydantic. We're going to anticipate a Pydantic object, and we're going to map that to the front end. Really easy. Then we're going to allow people to ask follow-up questions that do not follow that JSON schema. These are just like natural language responses. Interesting paradigm here. Like, you might be thinking that these are like different modalities that are going to be applied, and that's very true. These are 2 different modalities that we're going to pass through from an LLM. We know that a specific type of question relates to that data. So if we are thinking about intents and utterances, if a user says, I want to know more about data type, right? The backend will go, oh, data type detected. Let's hand that information through following the JSON schema. This is where we start butting up against problems because we want follow-up questions that don't follow that JSON schema. We want people to be able to ask, hang on, Mary, you just told me in that format this, and we want it to render differently. If we had used the technique that we discussed before, and we'd just handed it through in the prompt and we're going to only render the cards once, if the user has already seen the cards, do not render them again, don't render them again. Just show them once and then normal questions. Will it work? I tried it out for the sake of this. The answer is absolutely not, right? Absolutely not. The reason that this doesn't work is because we're trying to force like state-based interactions or like modal interactions onto an inherently stateless technology, right? The LLM, when you send a request, it's not storing a state somewhere invisibly in its processing. It's not going, I can tell that I've already shown the users these cards once, I'm not going to do it again. It's doing a calculation every turn. Context history may play a part in that, but it is not, strictly speaking, storing a memory artifact for that instance of interaction, right? It's not going, right, I've shown it once, don't show it again. Secondly, the other problem with this is the statement we're given is slightly ambiguous. There's a contradiction present in it. It's like, number 1, do show the cards. Number 2, don't show the cards. So you're creating a tension with those 2 statements. And ambiguity normally leads an LLM to err on the side of caution. So what you'll see is something like this. You're going to see that cards are being presented twice. It's always defaulting to the passing through that data object in that way, which is not what we want. What we actually need to do is handle this slightly differently. What we need to do is introduce an object called cards shown in the front end, right? We track cards shown as an application state from the front end, hand that to the back end, and use a multimodal prompt that switches out information within the prompt template based on the application state from the front end. This is a pretty hacky way of getting around this. You wouldn't do this at scale, you wouldn't do this at graph, but it demonstrates a core concept here, which is task pattern representation. Instead of handling one prompt containing 2 contradictory ideas and letting the LLM determine which is which at any given time, we handle that bit programmatically. We use data flags to trigger different instructions based on what's happened in the front end. The LLM isn't keeping track itself. It's not going to do that. We need to handle that bit for it and pass that through. Crucial to note here, we've basically just ironed out the difference between an application with a single LLM call and an agentic system. Our agentic system is able to use data types from the front end to persist state. Normal call, not going to do that. You just slap in the prompt. Remember this, give yourself a point every time this happens. It's not going to persist points. It's not an agentic system. So what we're doing, we're avoiding giving those contradictory task pattern representations. So you remember in the first prompt, we were saying two contradictory things. Under this set of circumstances, do this. Under this, don't this, but they're related. That interrelation causes confusion, and it means that more often than not, utterances from the user containing specific high saliency tokens are gonna trigger the data form that we're looking for every single time, and you're going to get repetition, and that looks bad. And let's be honest, there's one thing our users know, is that if it looks like an old school chatbot that's going to put them in a loop, they aren't going to interact with it. And we're in the situation where like the design language of these solutions is playing against us. It looks like a chat window, they feel like they know what to expect. That's slowly being broken down over time, but it's still an issue that we don't want to compound with our designing. This is real bad stuff. Let's return to our dice rolling scenario, and let's look at these prompts a little bit. And let's look at the first case. So you know the first case, we kind of told it, right? Get a deep contextual understanding of whether the user wants to roll dice or not. Only roll dice when you've been asked to. And sometimes it was working, sometimes it wasn't. All a bit strange. Not really. So what's going on here is that a lot of the models that we're using these days allow for reasoning. So what they'll do, they'll kind of break an input down into chunks, and then adjust each chunk in sequence, right? It's still probabilistic, but it gives you a much higher probability of returning a positive outcome. What it isn't is a way of forcing an LLM to do a specific thing in a specific sequence. If I tell it, right, only do it in these cases, it is going to err on the side of caution because we have that ambiguity again. We have conflicting instructions. What's a better way of approaching this? There are some, and here's one that I'm going to show you now. So you remember in the other application that we looked at, we were using like a state passed from the front end to inform what we do. In this application, through our prompt, we're going to give the LLM access to a short-term memory space, a scratch pad, where it can write its reasoning to as it goes. What you're going to find here is that this dramatically improves the rate at which the LLM calls tools successfully. Here's how it works. So we've got the scratch pad prompt. The user's free-form inputs embedded into that prompt that asks the LLM to reason for a set of questions. So we go, what is the user asking for? Does it involve rolling dice? If yes, how many dice? If no number is given, is the default one appropriate, right? So here's why the scratch pad's more reliable at structured decision making. So we know that LLMs are more reliable at structured decision making when they reason step by step. So as reasoning models, they give better outcomes, better probability. The scratch pad pattern gives an explicit space to think through a set of guiding questions before committing to a structured output, right? This massively reduces the chance of the model misclassifying intent or hallucinating parameters. The chain generally follows 4 steps, right? So we take the freeform input, we pass that, embed it into a prompt that asks the LLM to reason through a few steps. So like, what's the user asking for? Does it involve rolling dice? Blah, 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 blah. The LLM is then required to respond in a strict 3-field format, in the same way as we were looking at our JSON responses for the cards, right? We've got a schema and we're going to interpret that. Past Scratchpad, we're going to make a function that extracts 3 fields from the LLM's text output into a Python dictionary. Then we have a Boolean for should roll, we have number of dice, which is an integer, and then we have reasoning that's kept as a string. You see how we're working with these data classes as like objects that we can manipulate? Way better than just handing a text response and letting the LLM do the business. We then have routing, and we have a summary that's generated by a second LLM call. Why this works? We're splitting the thinking, right, from the doing. Pretty key. Without a scratch pad, the model is just going to predict the next token in the sequence, right? And even though if it breaks it down to chunks and it reasons in chunks, it could jump straight ahead to like call weather API cities, call Paris, based on like a super high saliency token within the first bit of reasoning. With a scratch pad, the reasoning is broken down, and then we have the tool calling. We have reasoning, right? Part of the pattern matching that we had before, to validation, and then tool call. Absolutely crucial to this. All of this leads to better task pattern representation. But the serious benefit happens at scale. So tool calling gets really, really hard when you need to like return data, process data, call another tool, move around all these things, really complex like structures in our agentic system. Without this solid task pattern representation and that low duration memory space, the LLM can forget the immediate constraints and then mix the reasoning into the tool JSON, collapse steps together, it can become really problematic. So giving it that structured representation reduces unnecessary calls, very important, and saves latency and cost. So the scratchpad is giving the model more tokens to form its decision space, right? So as it works through the decision surface, there's more material there for it to understand. So more tokens generally means that you've got more gradient resolution over the action boundary. That's complex. We're just improving the math. If you want to get super technical, what we're doing is forcing intermediate latent representations into the communication channel. There's a lot of precedent for doing this in software engineering, and all of that holds true here. All we're trying to do is change the entropy structure of generation. You're not going to understand that unless you're Moavii, but don't worry about it. Just know this is a good thing for our purposes. Hope you enjoyed this. Hope this has proved helpful. If you like to sync up on LinkedIn, feel free to drop me a message. I'm always happy to talk shop, and hopefully this will help you out with some problems in the future. Peace out.